Hello, everybody. Welcome back. So today we're going to be looking at volcanoes. So this is the last section for dynamic Earth. We're going to be looking at volcanoes in terms of, we're not going to be looking at all the different parts and things like that, although you're more than welcome to research it and I'll show you how to do that. But what I really want you to focus on is the processes, the dynamic Earth processes that we've talked about that can form volcanoes. So we'll look at where they're located. We'll look at the characteristics of a volcano. What is it dependent on? And what I'm hoping that you'll see is that for volcanoes are a lot like real estate. It's all about location, location, location. Um, and the location has a lot to do with the type of magma that is produced, and it's the magma that makes the volcano, not the volcano that makes the magma. I know it seems kind of counterintuitive, but it's the characteristics of the magma that forms the volcano. And the characteristics of that magma is in part determined about why it forms or where it forms. And so we're going to go through lots of information here. I'm not going to go spend a lot of time on this, so we'll get through it as quickly as possible. There's lots of little things that you can click on, and little videos that you can watch independently. I'm not going to show them here. I'll show you a few things, but please make sure to take a few minutes and just kind of look through those. Let's talk about plate boundaries. Most volcanoes form, of course, around plate boundaries, but which plate boundaries? So we have three: transform, divergent, convergent. Transform boundaries, you don't have subduction, you don't have the crust spreading out very thin. So around transform boundaries, you really don't have volcanoes. We just don't have the processes there to create them. The ones that do, though, divergent and convergent. Start real quickly with divergent. Divergent boundary means that the crust or the plate is being pulled apart. Where those plates pull apart, you have very thin crust, and so magma can, of course, reach towards the surface. For example, at the mid-ocean ridge, plate boundaries are being pulled apart, and you can have volcanic activity along that ridge where the crust gets very thin. In a rift valley, it's the same thing. A rift valley is a divergent boundary on continental crust. Again, plate boundary is pulling that crust very thin. It allows material to magma to get very close to the surface, and so you'll have volcanic activity along them as well. The other type of boundary, convergent boundaries, is also where you get your volcanoes, but only the subduction boundaries. So in continental collisions, there's no subduction, and so the continental crust, really just pushes up to form mountains. In subduction, you have oceanic crust being forced back into the mantle. As it goes into the mantle, you can see right here, as it goes back into the mantle, it carries with it millions of years worth of debris that is piled on top of it. Think about diatoms, which are a type of algae that have a carbonate shell or a silicate shell. There are living creatures that make shells using minerals that are dissolved in that groundwater. Once those organisms die and they pile up on the ocean floor, if they're near a subduction zone, they're getting pushed into the mantle as well. And so that material is going to affect the consistency of the magma. It's going to change its characteristics along with the water. There's going to be some water that's going to be trapped in little pockets as it's pushed down into the mantle, not to mention the water that's already built up in those minerals, chemically mixed in. So that's going to have an effect on the volcano itself. So plate boundaries, you're going to have your divergent and your convergent subduction volcanoes. So this one is continental crust, oceanic continental collision, subduction there, or oceanic collision volcanoes as well. So in this little animation is just to show you volcanic activity, recent volcanic activity, and hopefully you're seeing, and you already know the pattern, that most volcanoes occur along plate boundaries, especially what's called the Ring of Fire, which is actually just the outline of the Pacific plate. Lots of subduction happening along the Pacific plate. And a lot of you have already made the connection that it seems like the Pacific ocean is closing up because of all that subduction. The crust is getting eaten away, and you're absolutely right. And that the Atlantic Ocean is actually getting larger because of all the ocean spreading. And that's absolutely right as well. But it's along those subduction zones that you have your most powerful volcanoes, but you also have them along those divergent boundaries as well. So here's some important ideas that I want you to get out of this. What fuels volcanoes? Magma, what are its characteristics? What is it dependent on? Something called viscosity, or how a measure of how easily something flows. That has a lot to do with the type of volcano that is made from the magma, types of volcanoes, and then hotspots, which are volcanoes that are not located at plate boundaries. They have their own little separate piece. So, introduction. On May 1980, Mount St. Helens erupted. What triggered the eruption of Mount St. Helens? So, hopefully you've watched the video in class. If you haven't, you can watch this one here. Mount St. Helens is a part of a subduction area where a very small plate called the Juan de Fuca plate is colliding with the North American plate over on the west coast. It's a very small subduction area, but it has the potential to create some very powerful volcanoes, as we saw in 1980. Mount St. Helens is just one of the volcanoes located there. There are others as well. So what is a volcano? A volcano is just a weak spot in the Earth's crust where multi-material or magma can come to the surface or close to the surface. They are spectacular events, but of course they can be very, very dangerous. And it really just depends on the volcano, which is dependent on the type of magma. We'll talk more about that in a minute. They are both constructive and destructive. They make new crust or new land. The ash that can come out of volcanoes can cover the entire planet and drop global temperatures. But at the same time, it can provide nutrients for plants, grapes, things like that growing on the side of a mountain that need those really readily available rich minerals. So constructive, destructive. Over the past 10,000 years, there's been about 1,500 different volcanic eruptions. Anatomy of a volcano. So there's lots of parts to volcanoes, and you can see this diagram. We've got eruption clouds and eruption column, the vent, fumaroles, pyroclastic flows. Got all these different parts to a volcano. I'm not requiring that you know all of these. If you're interested, you're more than welcome to do some research. If you follow that link, this takes you to a nice little interactive, and you can look at different parts of a volcano, different terms relating to volcanoes. And you can just kind of thumb through them to look at some of these different things. But I'm not requiring that you know all of these. I really want you just to make connections between the characteristics of the magma and the type of eruption and type of volcano. So here's a little video clip called Volcanoes 101 by National Geographic. It's very straightforward. Please watch it when you get a chance. Really interesting material in there. But I'm going to skip through so that we can keep going. Now, all volcanoes are fueled by magma. Remember, magma below the crust, lava when it reaches the surface. But all volcanoes are fueled by magma. Now, magma forms from melted rocks. Pretty simple. Which melt around 800 to 1200 degrees Celsius, about 2000 degrees Fahrenheit or so. Now, these temperatures really start to exist at the bottom of the lithosphere and the top of the asthenosphere. So as subduction is occurring, when it gets below the lithosphere, that's where the melting starts to happen. Maybe a little bit before then, based on the characteristics of the magma and its silica content and water content, but it's around that area. Remember, as you get deeper in the earth, the pressure and temperature increase, but it is so hot in the mantle, so pressurized in the mantle that the material there is solid. Magma is the big thing that I need you to understand because it's the magma that makes the volcano. And because of that, there's factors that affect magma, that affect the consistency of the magma, that affect its viscosity, that affect its melt point. So here's some of those factors that affect magma. One, of course, is pressure. The higher the pressure, the higher the temperature required to make it melt. That's why the mantle is solid. Once the pressure is decreased, as that material gets closer to the surface, then it can become a liquid. Number two is water. A lot of people don't think of water being in a rock. I read this story to my kids. It's like Mickey Mouse and the giant, and he's trying to get rid of the giant, and he asks the giant to squeeze water out of that rock, and of course, the giant can't squeeze the water out of a rock. Then Mickey, of course, picks up, I think it's cheese, probably like mozzarella. You squeeze it, a little bit of water comes out, and the giant gets all scared and runs away. But rocks do contain water. They can contain water in the porous spaces in the rock or as part of its chemical content. The more water, of course, the quicker it's going to melt. A wet rock will melt at a lower temperature than a dry one. All right. Now, magma is this slushy mix of molten rock. There's gases dissolved in there. There's water content, of course, mineral crystals. The elements that are found in magma are the same ones that we find on Earth's crust. So most notably, oxygen, silicon, aluminum, iron, magnesium, carbon, calcium, potassium, all of those are still there. What are the two most common elements on Earth's crust? Oxygen and silicon. Silicates, the largest mineral classification. Quartz, for example. There's lots of others as well, but silica content has the greatest effect on magma characteristics. Beyond pressure, beyond water, silica content. Silica affects its melting point and how the magma flows. It's kind of like adding sugar to water. A little bit, not going to make much difference. You start adding a lot though, and it becomes stickier and stickier and stickier. Because of that stickiness, it doesn't want to flow as easily. That's what silica does to rocks. So silica, the most plentiful mineral on the planet, the more of that is in the magma, the stickier the magma, the less likely it wants to flow. There are three types of magma, all based around silica content. Okay, first type, basaltic magma. Basaltic magma is about 50% silicate content. You'd recognize it immediately if you were from Polynesia, around the Hawaiian Islands. The silica content is pretty low. It says 50%, which seems kind of high, but it's actually pretty low. So basaltic magma is very runny. It, because of that low silica content, has a low viscosity. So it just means it can run very smoothly. Very common in Hawaii and other places around oceanic crust. Remember, oceanic crust is made primarily of basalt. This is why, because the magma is very low in silicates. You can see in the picture there, it can be very hot, but it's very smooth. So there's a cute little video here about Hawaii and Hawaii's culture. But what I want to show you, of course, is this lava flow here. It has a cool name. It's called Pahoehoe. It's very smooth, very runny, very low in silicates. The AHA lava up here, the AA, it's AHA. It's actually a little bit cooler, so it's a little bit chunkier. But again, very low in silicates. Still runs actually kind of smooth, but it's just kind of crumbly and runny. It's really neat. The second type of magma, andesitic magma, cools to form a rock called andesite. Think Andes Mountains. This is higher silica content. So now we've got this higher silica, the magma is stickier. And because of that, as the magma comes up to the surface, it gets stuck. It sticks. It builds up pressure. The gases that are in it try to bubble out because of the decreasing pressure as it rises, but can't because of the high silica content. Pressure builds up too much, explosion. As it reaches the surface and all those gases kind of try to come out, but they can't. Once the pressure builds up enough, then it can force its way through the crust, of course, and create a volcano like Mount St. Helens. Mount St. Helens is a great example of andesitic type magma that builds up pressure that's higher in silica content. Last type of magma is called rhyolitic. If you remember back to our rocks, rhyolite. Rhyolite is almost the exact same mineral composition as granite. The difference is that it erupts. It cools off very quickly. So rhyolitic magma has the highest silica content. It's so sticky, most of the time it gets trapped underneath the crust and cools to form granite. But when you have these high silica content volcanoes, they can erupt extremely explosively, especially those that tend to form around or in continental crust. So picking up all of that silicate material in the continental crust. So very high silicate, very viscous, very thick, sticky magma. Builds up a lot of pressure. So I've said this word a few times. Viscosity is just a measure of internal resistance to flow. So the amount of silicate affects the magma's viscosity. Low silicate, low viscosity flows easily, basaltic magma. High silicate, high viscosity, very sticky, builds pressure, andesitic and especially rhyolitic magma. All right. Temperature can also affect viscosity. The higher the temperature of the magma, the more smoothly it can flow, especially places like Hawaii where you can actually see these lava flows. It's very hot, but because of the low silica content, it can flow very easily. So I want you to do some quick exploration. I want you to look at something called the VEI, or Volcano Explosivity Index. There's a couple of links for you here. Volcano Explosivity Index is just a measure of volcanoes based on a couple of different things. And so this goes into different eruption styles, but basically on the VEI, you can look at the plume height, so the column of ejected material, how high is that? The volume of material that's erupted is also measured and kind of correlated on the VEI. So the higher the VEI, the more the more dangerous it can be. So I included a couple of different links. So there's one, there's also this USGS site. It's actually the glossary for USGS, but gives you a good quick definition, but also this nice graphic showing you about the VEI, but also includes some different measures. So like Yellowstone, 600,000 years ago, the eruption of Yellowstone would have been a VEI of 8, very large. Mount St. Helens, VEI of 5. And hopefully you've seen in the video how big of an eruption that was. So VEI is just a measure of explosivity. It's using both qualitative and quantitative data to rank an eruption. As I said earlier, it is the magma that determines the volcano. If the magma is low in silicate content, low viscosity, smooth, runny lava, you end up getting one type of volcano. If the magma is very viscous, very sticky, very high silica content, you get different types. So let's take a look at each one. They're called shield, composite, also known as stratovolcanoes, and then cinder cones. These are just 3 types. There are others, there are subtypes. In geology or volcanology, the study of volcanoes, you really get into a lot of detail in these. We're just kind of basing it on 3. Start with shields. Shield volcanoes actually get their name from Shields, Captain America. Broad, gently sloping, formed from basaltic magma. So nice, quiet eruptions, easy lava flows, built up over time into a nice, gently sloping, broad, wide, big mountain. But it's all based on the magma. Low viscosity, low silicate, basaltic style magma. What type of crust would you typically expect to find low silicate content? And if you said oceanic, you would be correct. So I've got another little video clip for you on some volcanic eruptions, I think in Hawaii. Let's talk about cinder cone volcanoes. Cinder cones are really strange looking. These are real pictures. They are not fake. You can see why they're called cones. The cinders are actually pieces of volcanic material or debris, lava fragments, dust, let's just say ash, that pile up around a vent. So here we have magma that is higher in silica content. It's stickier. Gas pressure builds up and literally blows the magma apart, where it cools very rapidly and then piles up on the side. There's a cool story about a volcanic vent opening up in Mexico, a place called Pericuten, in the early 1900s. It was in a farmer's field, just opened up one day, and then over a year later, you had a volcanic mountain that looked like this. It's pretty crazy. So cinder cone volcanoes, higher silica content, the magma literally blows itself apart due to gas pressure, and it just piles up. It piles up, so it's really steep. It looks like a big anthill. So here are some of the pieces that can come out of volcanic eruptions: ash, cinders, which are pebble-sized pieces, all the way up to bombs. Bombs are the very large pieces that can come out of a volcanic eruption. So you typically see these in cinder cone eruptions, but also stratovolcanic eruptions. All right, so that brings us to the last one, composite volcanoes or stratovolcanoes. In these types of eruptions, there is very sticky, it could be andesitic or rhyolitic magma, so higher silica content, very viscous. What happens here is you have alternating styles of eruptions. So like to say both quiet eruptions like a shield volcano and explosive eruptions like a cinder cone. They're very dangerous because you can have both. You can have one or the other. They can, like Mount St. Helens, build up so much gas pressure, they can blow off the side of the mountain or blow it apart, like in Krakatoa in the late 1800s. That was an eruption event that was felt thousands of miles away. So these composite volcanoes are the magma is very thick, viscous, and sticky. But you have both types of eruptions, and they basically form alternating layers. So if you were to cut a section of the volcano, cut it in half and look on the inside, what you'd see is alternating layers of ash, cinders, bombs, lava. So it's almost like the volcano builds up pressure, blows out the ash, the cinders, the bombs, the pyroclastic flows, the gas comes rolling down the hill. And then right after that, the lava flows more smoothly, more quiet. And then it just piles up on the side. So it makes it very steep, pretty much looks like a mountain. A lot of people ask me, well, why is there snow on top there? Rock is a really good insulator, and there's pressure and heat underneath there. And if it happens that it erupts, that will melt very quickly, and you have what are called lahars or mud flows that can come rolling down, which are also very dangerous. But anyway, you could go skiing and then be in an eruption. Be kind of rough. Kind of cool day, but a very rough day. Hope you can ski really fast. So this is an example of a pyroclastic flow. A pyroclastic flow is just from an explosive volcanic event. Of course, magma content very high in silica, blows itself apart. But a pyroclastic flow is basically a cloud of ash that comes rolling down the volcano pretty doggone fast, 100 miles per hour or more. It could be 800 degrees on the inside of that cloud. It's definitely nowhere you need to be. The eruption of Mount Vesuvius that destroyed Pompeii over 1,000 years ago. most of the damage was from the pyroclastic flow. And just because I wanted to, I included some pretty cool videos like this one, I think it's Mount Etna, Erta, sorry. And somebody recorded a video of them throwing trash off the crater into the lava down below. I thought it was pretty neat. But you can see how it punctures the thin rock up top. It punctures straight through and allows the gas and pressure, kind of like a little mini eruption. And of course, this one, just because this dude is crazy, he climbs down into a crater to get as close as he can to the lava, which is just nuts. It's very nuts. Anyway, you're more than welcome to watch those. Last but not least, hotspots. Now, hotspots are volcanically active regions that are far from plate boundaries. So in this little map over here, you can see that these are volcanoes. Some are close to plate boundaries, but not all. Hotspots are very strange because they stay put. So we all know that plates move, all right? But a hotspot actually operates like this. It stays put where the plate rolls on top of it. And so because of that, if you look, you can look at the past eruptions, you can tell which way the plate is moving. Now, hotspots can occur under oceanic crust. They can occur up under continental crust. Because of that, their eruptions will be very different because of silica content. But hotspots, it stays put. The crust moves on top of it. It's really neat. For example, the classic hotspot in the Pacific, Hawaii. The Big Island of Hawaii is actually the most volcanically active. And you can see in this little diagram here, the crust is actually bent up. And so the hotspot stays there and it just pumps out new material and creates a new island. But the plate keeps moving. This island over here was actually the Big Island at one time, but the plate kept moving. So it will make a new volcano, and then as it moves away from the hotspot, you can see the pressure here allows it to sink, subsidence. So it kind of lowers back down because it doesn't have that hotspot pushing up on the crust, and of course erosion as well. So the Big Island of Hawaii, so where it's volcanically active, as you move away from the Big Island, they basically get older and older and older until they go up under the water. If you look below the water, there are others as well. It's part of the Emperor Seamount chain. It's very neat. Been there for millions of years. There's actually a new island forming, excuse me. There's a new island forming, not the Big Island. Eventually the Big Island will stop erupting and then we'll have the new island. What about supervolcanoes? Well, it's the same thing. It's a hotspot. Yellowstone National Park is a supervolcano. It is a very large magma chamber. It is a hotspot that stays put where the crust moves on top of it. But now it's erupting under continental crust. Continental crust, high in silica content. You get the picture. Can create a very, very large volcanic eruption and has for millions of years. We have evidence and we can see these ancient eruptions in the rocks there as well. So you're going to do more research on those two, on hotspot volcanoes. Again, these are away from plate boundaries. These have nothing to do with subduction or with divergent plate boundaries. They're kind of their own classification because they have their own unique, excuse me, formation characteristics. All right, that's all I've got to show you. Again, the big thing that I wanted you to see was that it is the magma that makes the volcano. The characteristics of the magma are dependent on the temperature of it, the water content, but especially the silica content. The higher the silica content, the more explosive the eruption can make volcanoes like cinder cones and stratos. The lower the silica content, the smoother, the runnier the magma, basaltic, you get shield volcanoes. Where we have this activity, subduction zones or divergent, really affects the type of volcano that you get. But also when it comes to volcanic hotspots, where they sit up under what type of crust also has a huge effect on the type of volcano that we see, the explosivity of that volcano. All right, hope you enjoyed. Hope you learned something. Please go back through and watch some really cool videos in there. If you have any questions, let me know.